All right. Well, happy Monday. Let me clear out my notebook. Okay, so today we will talk about NumPy. NumPy is a module that you load in Python. It adds a very important data structure that is not part of base Python, and that is the NumPy array. And in data science with Python, we use pandas, and pandas is built out of NumPy arrays. So pandas introduces another data structure called the data frame. We'll talk about that in an upcoming lecture. Those data frames are built out of NumPy arrays. So NumPy is very important. And so let's go ahead and take a look. All right, so you're going to need to import NumPy. Now, if you installed Conda, NumPy is, or if you installed Anaconda, NumPy is one of the packages or libraries or modules that gets installed with Conda. But if you don't already have NumPy installed, you can do like a Conda install NumPy or pip install NumPy. I guess some people pronounce it NumPy. I don't know. I'm going to pronounce it NumPy if that's okay, right? And when you want to load it, okay, if you want to make use of it, you always have to import it, all right? So when you start up Python, it does base Python does not load up NumPy, so you always have to kind of import it. And the convention is to call import NumPy as NP, okay? Because pretty much, to access any of the features or objects or functions within NumPy, you would start everything off as NumPy dot whatever nd array or whatever it is the function that you're going to do. And just to kind of save a few keystrokes, we're going to import NumPy as NP, and then we will just do NP dot whatever, okay? But pretty much, when you look up documentation for NumPy, it will always start off with NumPy dot this, function name. So always do import NumPy as NP, and that's just the convention. Everybody does it this way. Technically, you could import NumPy as some other set of characters, but I think everybody will find that confusing. So always just import NumPy as NP. You can ask for the version. I have 1.24. I think the latest is 1.26 or something. My home computer is like 1. It's probably fine. Okay. And so the data structure that NumPy introduced is the NumPy array. Okay. They are mutable. So they look kind of like lists, but they're not, okay? The key difference is that a list in Python, the base data type, can contain a mixture of objects. So it can contain, characters, string values, along with numeric values, along with, functions or anything else, other lists inside a list. A NumPy array can only contain one data type. So if you say, if you put in integers, the entire array has to be integers. If you put in floating point values, the entire array has to be floating point values. And so it is more restrictive than a list. This has the advantage of rapid increasing calculation performance, because with a list, it's kind of like, okay, well, I don't know what's coming next, and it has to kind of keep track of what the data type is in each of these things. Whereas the NumPy array, it just knows all of the values. You might have like a huge array with 1,000 by 1,000, a million values in there, and it doesn't have to worry about all of the different data types for all of these values. It just knows everything in here is going to be a floating point number. Okay, so we create an array. We can take a list or something else and create an array with it using the function numpy.array, okay, or np.array if you've imported NumPy as NP. And so here I'm going to take the list containing 1, 2, 3, the integers 1, 2, 3. We are going to convert this into a NumPy array using np.array. And it says, yep, this object is an array with the values 1, 2, 3 in it. When you print out an array, so here I'm going to again, take the list containing 1, 2, 3, convert it into an array using np.array. I'm going to store it as object A. And if you call print on A, the way arrays get printed out is with square brackets, but no commas to separate out the values. And compare that to a list. A list also uses square brackets, but the values are separated with commas. So this is kind of the key. I guess it's a little bit more of a subtle visual distinction between a list and an array, and because they both use, again, almost everything in Python is designed so that by visual inspection, you know what data type it is, right? Integers always show up, as integers, and floating point values, even if they are whole numbers, always carry a decimal, right? So like if you put in a float, but it's 2, it's going to always print out as 2.0 or 2 point at least. And then similarly, lists always have square brackets, tuples always have parentheses or curved braces, dictionaries always have curly braces. So just by visually looking at it, you should be able to tell what it is. And so here, to be able to tell that it is an array and not a list, even though they have square brackets, is that the array doesn't have commas, okay? And then when you ask for what is the type of this object, it's going to say this is an ND array, which is part of NumPy. So NumPy arrays, you can kind of, so you all took stats 20 and you're familiar with the vector, okay? The atomic vector in R can only contain one data type. And if you try to mix data types, R does this thing called coercion, okay? And it coerces everything, all of the things to be the same data type. The same thing happens with NumPy. This thing, we don't call it coercion, we call it upcasting, right? It upcasts, but it's the exact same concept, where if you're mixing different data types, because the NumPy array has the restriction that everything has to be of the same data type, the more restrictive data types get upcast to the less restrictive data type. So here we're going to create, here I have a list containing integers 1, 2, 3.0, a float, and Boolean values false and true. The least restrictive of these data types will be, is the float, and so all of the other values get upcast, okay? Again, same thing, idea as coerced. They get upcast into the least restrictive data type. So everything will get upcast into a float, all right? So false will get upcast into 0, true gets upcast into a 1, and these are all floats, and you can see that they are floats because they all come with little dots afterwards. So 1 point, 2 point, 3 point, 0 point, and 1 point. So this is the visual indicator that these values are floats. If I have 3 in quotes, this is a string, so everything will get upcast into strings. And so this is what we get. We get 1 in quotes, 2 in quotes, 3 in quotes, and true and false also get put into quotes there. We can have higher dimensional objects, and well, you know what? Let me check something. Have I created the view quiz for today? I don't know if I've done it. So if we want to create a matrix, like a 2-dimensional matrix, we can do that. In NumPy, this is still a NumPy array, okay? It's still an ND array, and here this is going to create an array with 2 rows and 3 columns. And if you inspect what is being put in here, I have a list of lists. I have one list with two lists inside of it. Each of those lists are length 3, right? So I've got the square bracket on the outside, and then within that I have a list of 3 and a list of 3. I've got 2 lists of length 3, and I'm going to just say make a NumPy array out of this, and so this produces a 2 by 3 thing, and it retains kind of this, it opens with 2 square brackets, right, indicating that the entire array is, 2-dimensional, and it consists of kind of these 2 rows with 3 elements each. Okay, if you try to do something like this, okay, you can create a NumPy array, but it's going to say, this is an array of lists, which is, it is a thing that exists, but it's not very useful, okay? So here we get, or actually, I think, I guess they've changed the behavior of this. No longer, so you can't do this anymore. Creating an array of lists of mismatched length. So this I will have to update if the dimensions. Well, okay, this is no longer the case. Now it just kicks back an error and says you're not allowed to do this anymore. Okay, there are a few things that allows us to kind of make a bunch of kind of arrays very quickly. So you can say, I want an array of all zeros, length 5, right? So this is the same as kind of creating a vector in R using repeat, right? And so here we're going to get a 1-dimensional array with 5 zeros in it. Okay. The default value type is floats. So so we have that, and so if you want to do integers instead, you can say data type of these zeros should be an integer, and you will get zeros instead, integers here. You can also create a matrix. So if you want to have a 2-dimensional thing, you can provide it as the argument for how many values you want. You can give it a tuple or a list, all right? And so this says I want 2 rows, 4 columns, and I get a 2 by 4 array here. You can also create, a higher dimensional thing. So this will create a 3-dimensional structure, 2 sheets, 3 rows, 4 columns each. So this is a 3-dimensional data structure. So you can kind of imagine I've got like I don't know, this funny, grid of cubes or something. Okay, and then and you can have like a 4-dimensional kind of like a what would you call this? So this would be not a cuboid, or is it a cuboid? Even if it's not like a rectangular cuboid, rectangular prism, and this would be kind of like your rectangular hyperprism. Okay, and so you have 2 blocks. Each block has 3 sheets. Each of those sheets has 4 rows and 5 columns. All right, and so this would be, this 4-dimensional data structure. I guess we might call these tensors. That's the name that Google gives to these data structures that are basically, they're just arrays. They're just arrays, but Google calls them tensors here. Okay, let me give you your first view quiz answer, but I have to unlock it. What did I do? Okay, our first letter is B. B as in bear. First view quiz answer. B as in bear. Okay. There's also the equivalent function np.ones does the exact same thing as np.zeros, except instead of 0, it does a 1. Okay, so that's I think that's pretty basic. And then, yeah. The first one was B. B as in bear. B is our first view quiz answer. Okay, I'll I'll put that in here. And then, and if you wanted some value other than 0 or 1, you can use np.full, and it does the behaviors the same. All right. So this is just a quick way to kind of create arrays of a certain dimension. If you just, if you don't really care what values go in there or something, right? I mean, or like probably a good initial set of values are zeros or ones. Zeros if you're going to do some kind of addition or subtraction operation, and ones if you're going to do any kind of multiplication or division operation. Those are probably your choices to go. Okay. We can also generate random values. Okay, you can generate random values, and so there is a library called random within Python, but NumPy also has its own set of random generator functions. Okay. And so there is, for reproducibility, you can do random.seed, okay? And so that will kind of set, some number. So your values and my values will be the same. And then numpy.random.random will generate values on the random uniform from 0 to 1, okay? And I think we're accustomed to the idea of generating random uniform values. That's going to be your random.random. And you say, I want 5 random.random values, and you have that. If you want values from, say, other distributions, like the normal distribution or things like that, or you want random integers, we have functions that do that as well. So if you want random normal, standard normal will be random.randn. Yeah, question. Yeah.
I can't access the new list for some reason. It's part of an unpublished module.
It's part of an unpublished. Okay, I have to. All right, let me publish the module. Sorry, I forgot to do this. Okay. My phone. Yep, that's not a published module. All right, now the module is published. I hope this works now. Okay. Now you can access. Okay. You got it. All right. So standard normal will be random.randn, and so values set, with mean 0, standard deviation 1. So basically your z distribution is going to be that. If you have if you want to generate values from the normal distribution, but not necessarily standard normal, so here you can specify that, and you can do random.normal, and here we're going to have mean 10, standard deviation 3, and then here I've just been putting in 5, but just like numpy.1s and numpy.0s, you can put in dimensions. You can put in I can put in a tuple saying I want 8 values in a 2x4 matrix, and we can do that as well. And so here we can see these are centered around 10 with standard deviation of something around 3 or whatever. Random int, you basically specify a range of integers. This is kind of like the range object. So you have a starting, and the starting value is inclusive, but the ending value is exclusive. So 0, 10 will really just go from 0 to 9, okay? And it's like, why not just do 0, 0, 9? That's just kind of how Python does it here, okay? And here we want 20 values, random integers between 0 and 9. So if you wanted to simulate dice rolls or something, you can do 1, 7, and that will just simulate like 50 dice rolls. There's a whole bunch of other random functions, and so let me load. So random sampling, numpy.random, and you can see I don't know. Okay, a whole bunch of kind of random sampling things. Read more about this, I guess. All right. So yeah, you can generate stuff from, like, say, the Poisson distribution or the beta distribution or the gamma distribution. And, you know, just like anything else, you just say numpy random beta distribution or something, right? You just go online and you search, and you can look up. All right, here's numpy.random.beta, I guess, and there, look at all of these things. Beta, binomial, chi-squared, Dirichlet, exponential, F, gamma. I don't even know half of these distributions. What's the Rayleigh distribution? What does that do? Weibull or generalizations? Okay. I don't know. I don't remember learning about this one. Weibull distribution. Oh, when do we use that? That's like product failure or something time, I think. All right. Sequences. Okay, so we're already familiar with the range object. Range object 0, 10, 2, that will go what? 0, 2, 4, 6, 8, right? And that's that. You have basically the same thing from NumPy, but it's going to create an array, and so you call arange, numpy.arange for arrays with these things, and they work pretty much identically to the regular old range thing, except it's going to create a NumPy array of these things. Okay, and so you can also create the range object and then put it into NumPy array. That's not as efficient. So to do that, so you can do this, and this will go from 0 to 100 by step size 5, so ending at 95. And then if you just need like a 20 values going from 0 to 19, you can just give it with one integer here, np.arange, and you'll get an array going from 0 to 19. And this is going to be very, very common. So you'll see that for I in numpy.arange, whatever, 1,000, 100,000 or something. Okay. We also have this function that creates linearly spaced values, all right, which will give you the length of how many things. So it starts at the thing, and here's where it might feel a little bit confusing. For lin space, the ending is the stop is inclusive. So here I'm going to say, give me 11 values starting at 0, ending at 100, and I want these linearly spaced out. So we want the space between the first two values to be the same as the space between the last two values. And so if you do this, you're going to get 10. Now, a common mistake is to say, okay, well, I want to go from 0 to 100, but I want to have 10 things. So that's actually going to space them out 11.11, right? So you get you end up getting this. Now you can specify, say, endpoint equals false. This gets hard to kind of keep track of in your head, though. Okay, so 0, 100. I want 10 of these things. Endpoint false will go from 0 to 90. Okay, but if you say 0, 109. The last value here is going to be 88.888. Okay, it's basically the same thing as doing it with one higher value where endpoint is true, and then you drop the last value. But I think you have to sit here and think about, like, what is the last like if I said do this 0, 100, 9 endpoint equals false, you have to like do a kind of like a bunch of like mental math in your head to figure out like the last number in the sequence is going to be 88.88. So my personal recommendation, don't bother with endpoint equals false and just kind of figure out what these things are, right? Arrays have attributes, okay? These are basically the properties of the array, and the most important ones are the number of dimensions. So if it's basically kind of like the equivalent of a vector, that's a one-dimensional array. If it's a matrix, it's a two-dimensional array, or you might have something like that. The shape will actually give you what those dimensions are. So ndim is the number of dimensions, but not the dimensions. Dot shape is kind of the equivalent of when you call dim in R and it asks, it's 2 rows, 3 columns, or whatever. That's going to be shape. So here, I'm going to create X is going to be an array of ones arranged in 3 rows, 4 columns. I'm going to print that out. Here is my thing. All right. So one thing you might have noticed is that when you don't call print, it returns the object itself. And when it returns the object itself, it wraps it around inside kind of this indicator that says array. Whereas when you print it, it comes out printed like this. Okay. So what is number of dimensions on this thing? Okay, well, it's two-dimensional because we've got rows and columns. So x.ndim is going to be 2. This is a two-dimensional structure. The shape is going to be this tuple, 3, 4. All right, so it's basically how many rows, how many columns you have. And here, what is our data type? The values in here are all floating point. And it's going to say floating 64 because these are 64-bit floating point numbers versus, which is generally your double precision floating point number. You have other options. You can have 80-bit floating point numbers. That would be a long float, and then you can have single precision, a 32-bit floating point number. By most of our calculations are all 64-bit floating point numbers. Okay, so what is this? np.arange 0, 12, 1. How many values am I going to get here? And what will this look like? What are the dimensions of this? Yeah, go ahead. Yeah, we're going to get 12 numbers, starting at 0, ending basically at 11 here. And we've got a one-dimensional, basically just a kind of like a vector, right? We don't call them vectors, that's R, but a lot of you I think are familiar with R, and so basically like a vector, but this is a one-dimensional NumPy array. So when you ask what is the dimensions on or number of dimensions, it's going to say it's one-dimensional. Okay. Now, when you ask for the shape, you are going to get a tuple with just 12. This is not a 1 by 12. It's not one row with 12 columns. It's just a length 12 array because it's one-dimensional. So it's a tuple with just the value 12. And to indicate that it's a tuple, you get a 12 comma. You can take an array and you can reshape it. Okay, so this will kind of reflow the values. So here here's my one-dimensional array, and I'm going to reshape it into a two-dimensional array with 3 rows and 4 columns. Okay, you can do something similar to this in R, right? You can take a one-dimensional vector and you can basically add dimensions to it, and it will kind of reflow the values into a matrix. So same kind of idea here. One key difference is that if you were to change the dimensions in R on a vector into a matrix, it arranges them column-wise. Python does it row-wise, right? So that's just a design choice that Python made versus the design choice that R made. And so here, that's just something, as you're kind of like converting, like, how do I do this in this language? How do I do this in that language? You just have to be aware of these differences here. But you can take that, so this one-dimensional array, rearrange it, reshape it into a two-dimensional array. Okay. Now this does not, this returns a new thing. So almost all of the NumPy functions return new objects and leave the original objects unchanged. That's a difference from, say, like in Python, a lot of these methods that affect lists change the lists in place, whereas in Python, most of these functions, their default behavior is to return an entirely new object and leave the original object unchanged. So here, if I ask what is the original object j, it is unchanged, and I can call it, j.reshape and give it this tuple 4, 3. Right. So here, notice there's a couple ways I've called this. Right. So I can call the NumPy reshape function and put j in as an argument along with the dimensions, the tuple of dimensions that I want it to change into. I can also use the reshape method in the j array, right? So j is a NumPy array, and it has its own methods. So this is kind of like list.append, the methods associated with the object. So there's kind of two ways to kind of do the same thing, and here I'm giving it as multiple arguments the dimensions that I want. Again, the function here leaves j unchanged. So this is going to return basically a new object with these dimensions that I provided, whereas j, the original NumPy array, is unaffected. K, remember K is the result of this, so this is 3 by 4, and so I have my thing here. You can ask for the transpose. The transpose is an attribute of a NumPy array, and you would get K dot T, okay? And that will be the transpose, and it does, well, it transposes the matrix, and I think that behavior is exactly what we expect. Okay. Again, K dot T is an attribute. It's not a method. It doesn't, these NumPy methods generally don't modify the original objects themselves. So K in its original form is still there at 3 by 4. You can chain a lot of these methods together. Okay. So I can create so see if you can kind of follow along these steps here, okay? So we're going to create a range object, length 12, step size 1. I'm going to reshape it into a 3 by 4, and then I'm going to transpose, right? So you often see this kind of chaining of methods because each of these things return basically a new NumPy array, and whenever you get a NumPy array back, it comes with its own methods that you can then kind of run. So basically, at the end of this whole thing, after transposing the 3 by 4, I'm going to get a 4 by 3 array, and this time the values will be filled out column-wise. So I have this 4 by 3 filled out where the values are arranged column-wise. Okay. Here, sometimes in Python, you will see this -1. Okay, you'll see this -1 thing. And it feels confusing, right? We're asking to reshape this array j. So j is a length 12, one-dimensional array. And here we're going to say reshape it to 3, -1. Okay? What is the -1? Well, the -1 basically says, Python, I want you to rearrange it so the result will have 3 rows, okay? But I don't want to be bothered to calculate how many columns, right? Because if I said rearrange this length 12 thing into, say, a 3 by 3 or a 3 by 5, like if I say like 3 by 5, it says I can't take this length 12 thing and arrange it into a 3 by 5. That's not going to work, okay? So you do 3 by -1, okay? And -1 is basically just kind of like a placeholder for I don't know the answer right now. So it just says I know I want 3 rows, and use however many columns you need. Okay, and so Python's going to say, well, I got 12, so we're going to figure out, and it's going to be arranged into 4 columns here, right? And so this is often handy if you have some undefined, like, in your function, you want to allow for vectors or arrays of various lengths to come in and then to be rearranged without necessarily knowing exactly how many values you're going to have. And you can put this -1 wherever it needs to go. So I can do -1 comma 4. This means I want 4 columns and however many rows it takes. All right. And then it can even be in higher dimensional things. So I could say 2 comma -1 comma 2. So this means, the first dimension is basically how many sheets, and then this will be how many rows and how many columns. So now I know I have 2 rows, or 2 sheets and 2 columns. How many rows do I need? We're going to need 3 rows. It's going to figure that out, but it does that as well. Okay, and again, it fills it out rows, then columns, then sheets, and kind of that order there. Okay, so here is another another array, Y. It's a one-dimensional array. What is the shape of this thing? So if I call y.shape, it's going to return a tuple of its dimensions. And so just to review, pop quiz, you just learned this 5 minutes ago, but it takes a little while. So what is the shape if I do y.shape here? Yeah. 12 comma, a tuple, and it's going to say it's just length 12, okay? So here's a question. What will happen if I transpose y? The behavior here is different from, say, in R, when you take a vector and you transpose it, R turns it into a matrix and then makes it a column, okay? Here, Python goes, what do you mean? You can't transpose a one-dimensional thing, or transpose of a one-dimensional thing is basically itself. So when you do y.transpose, it's still just a length 12 one-dimensional array. Okay, so y.transpose is it's not going to suddenly add a second dimension to it, and you can even see y.transpose.shape is going to be 12 comma. Okay, whereas if I reshape this into a matrix with 1 row, 12 columns. Okay, so subtle distinction visually, when you print out the one-dimensional array, there's only one opening square bracket, okay? And here, this is a matrix, but it's a two-dimensional array, and so we have 2 opening square brackets, okay? And even though I don't have a second row, this is now an array with 1 row and 12 columns. And so when I ask what is the shape of this, it's going to say 1 comma 12. And so when you transpose this, basically you're swapping the positions of these dimensions here. So the transpose of Z will be 12 rows, 1 column. And if you ask what is the shape of Z transpose, it's going to be 12 comma 1. Right? So that's an important difference here. Basically, if it's a one-dimensional thing and you ask for the transpose, it's still going to be one-dimensional. And if you really want to actually transpose it and go from a row into a column, it needs to be two-dimensional. Okay, let me give you your second view quiz answer. Second view quiz answer is the letter A. A as in apple is our second view quiz answer. Okay, we can slice arrays, we can subset arrays. Works almost the same way as slicing and subsetting lists. So here is here's our one-dimensional array. We're going to say, hey, give me the index 4 position. Index 4 position is the 5th item, which is just also 4. Y.shape is that, and I can say, hey, give me values from 4 to 6. So we're going to get, what, 4 and 5 back, okay? And it's going to be an array there. You can also basically do, start colon step. So I can say, give me from index position 1 up through index position 8, step size 3. So we're going to get 1, 4, and 7. You can give it nothing, and that will basically start off at kind of 0. And we can say, hey, end at 100, give me the every other value. So that's just the even values. I mean, we could have just done 0, 100, 2 to get the same result as well. Okay. We can subset. We can subset higher dimensional things. For whatever reason, I provided a list, but yeah, instead of a tuple. But we'll take our 12 values, reshape them into a 3x4 matrix here, NumPy array with 3 rows, 4 columns, and you can ask, you can subset higher dimensional arrays with square brackets here, and here we're asking basically for row index 1, column index 2. So what is that? That's going to be the value 6, right? And it's going to come back as a as the numeric value there, right? So here we're going to get 6. So one thing to note here is that if you're just pulling out one value, okay, and I don't know if we gave it any thought here, but when we just pull out one value, it's not actually an array. It's just the value itself. So here it's just saying, hey, it's the integer here, okay? But you can also provide a slice or a range of values. So we're saying, hey, give me row index 0 to row index basically 1, and column index 0 to column index 1. And this will give me basically the 2x2 array of the top left corner. Okay, so here this is our original thing, and we're going to get basically out this 0, 1, 4, 5 right here. When I ask for what is this z? Okay, you can also say, hey, give me row 2, all of the columns. So you'd specify comma, colon with nothing in front or behind it. So that's basically just slicing out the entire row. Row index 2. Okay. What is the shape when you slice this out? The shape of this is it's a one-dimensional thing. It's just a length for a NumPy array. Same kind of thing here. Here we can slice out the column with index 2. So we're going to get 2, 6, 10. And again, this is also one-dimensional. So it's just the column. It's going to be, I guess column isn't the right word. It's just going to be these 3 values in a one-dimensional array, 2, 6, 10, length 3. So I think this behavior is expected. Maybe the only difference between, say, NumPy and R is that in R, if you just wanted the entire row, you just leave it blank. You just do comma blank. And here, if you want the entire row, you do comma colon with nothing in front or behind it. Okay. When you do a slice, okay, these are actually view objects. Okay, so we've seen dictionary view objects, which are kind of these dynamic, I guess, views of these things, right? So the dictionary is mutable. We have the view objects, say like dictionary.keys, and when the dictionary gets updated, that view object that shows what the keys are in that dictionary also automatically reflect those changes. So here, Z is going to be this array, 3x4 array, and I'm going to basically subset basically the first 2 rows and first 2 columns. So we're just going to get this 0, 1, 4, 5. Right? Here I am modifying. The arrays are mutable, so I'm going to just say change the value in index position 0, 0 to the value 99. Okay? And so if I ask what is Z now, the top left value is 99. And if I refer to what is Z underscore sub, which again is the view object pointing to the top 2 rows and top 2 columns, or first 2 columns, it reflects that. So it's the view object itself reflects the change, even though I didn't like redefine what Z is. So when you subset this will be this will create a view object. It's all, unless you like explicitly kind of copy those values or something. Okay, here. So notice here I modified the object z, and I said I want to change the value at 0, 0 to 99. Okay, this I am creating an entirely new NumPy array. I'm creating an entirely new NumPy array, 15 values, 3 rows, 5 columns, and I'm going to take the name z and have the name z point to this entirely new object that I'm creating. Okay, so z now is this 3 by 5 thing. Okay, this view object though still points to the top, the 2 by 2 corner of this, unfortunately, like this object in memory that no longer has a name to it. Okay, but this thing z underscore sub still refers to that thing, and so this thing still reflects 9914. Okay, and whatever this original 3 by 4 thing, even though there's no name to it, it's not going to get collected by the garbage collector because Python recognizes that we still have a view object referencing kind of the top left corner here. It's just I have nothing. I don't have a name to kind of get a hold of the rest of the object either. So that's what you have. If you want this thing not to be a view object, you can do .copy, okay, and that will have the copy effects. Okay, so here is z. Now it's a 3 by 5. We can still reference the top left corner of 0146, but this will be .copy. Okay, so this will be 0156, and so now if I change this top left value to say 55, the copy still contains 0, but that object z, the top left value, is now 55. Right? So I think this behavior makes sense in that we recognize, I guess, just we have to kind of remember some of these behaviors where when you slice out a thing, you're not getting a copy, you're getting a view object. And if you want a copy that doesn't, is no longer associated with the original thing, you have to explicitly call copy on it. Okay. If you do slice out this view object, if you change the view object, it's also going to change the underlying thing. Okay, so the view object is not like read only. You can look at the view object and you can change the stuff in there, and that actually also changes the original array that the view object is looking at here. Okay. The view object themselves, if you ask for the type, they are also arrays, and they contain all of kind of the methods and attributes of arrays. So if you have, with this view object, we can transpose it, we can reshape it and stuff like that. But again, these methods, transpose and reshape and things like that, don't actually affect the objects themselves. So the view object is still 99.1,4. All right, let me give you your last view quiz answer for today. Question 3 is E, and that is it. And that is that will be it for today. Have a great rest of your day. We'll see you Wednesday, and yeah, till then.